Good morning to all. Welcome to the last day of this very intensive 5-day workshop. I'm Nagarajan. I'm a professor in the Department of Chemical Engineering here. I'm also the Dean for International and Alumni Relations. And I'm going to be chairing the first session this morning. The theme of the session is Why Computational Brain Research, Future Challenges to Software Development. And our first speaker is Kris Gopalakrishnan. Since we are already about running 10 minutes late, I think we'll go ahead and get started. Kris, of course, needs no introduction, and I will ask him to start his presentation.
Thank you, Nagaraj, and good morning to every one of you. I think you have had 4 days of very intense discussions, and I'm very glad at least some people are still left in the room after 4 days of intense discussion. I think every day we were starting at 10, and today we decided to start at 9. I think people have still not got accustomed to coming at 9. But we'll get started because we have I'll have waiting actually on the video conference. Of course, I want to start by welcoming participants from industry. I want to make sure that they join this effort either at IIT Madras, hopefully at IIT Madras, but other locations also. We have significant representation from Indian Institute of Science. We have 3 chairs at Indian Institute of Science also, plus of course the Center for Brain Research that's coming up at IISc. And soon there will be a center coming up in NCBS also. So we need to try and link up all these together because the larger the community, we can take on larger and larger problems. So that's the reason. And I want industry participation significantly increased. We want to show that in India, industry does support research. That's being questioned at this point. Tatas have been at the forefront of this way back, actually, long back, in setting up several of the leading research institutions in India. Even NCBS, of course, is an offshoot of TIFR, which is set up by Tatas. IISc is set up by Tatas. But we need a lot more participation, and we need to re-engage with the Tata Group. I strongly feel that global collaboration in research benefits everybody. We have a large talent pool in India. This is the same talent pool that's actually feeding into the rest of the world, and hence I strongly believe that you will get access to the talent pool much earlier, and you can shape that talent pool much earlier by creating capacity in India. We can jumpstart the quality of research that happens in India by this collaboration, and that's what this week is all about actually, the collaboration and jumpstarting the research that is happening here being integrated with the rest of the world. I strongly believe that it's win-win. We create more capacity for research around the world. We get faster and affordable solutions. I always, whenever now I meet a foundation, I tell them that if you spend $5 outside India, especially in a developed country, if you spend $1 in India, you can double the research output. That's the power of this win-win relationship. And I think we need to talk about it. Everywhere research dollars are becoming scarce. So we're combining our hands. And the $1 in India doesn't have to come from outside India. That $1 from India now should come from India itself. I think we need to collaborate, and we need to make this win-win solution now work for everybody. I think that's the opportunity I see, and that's why I'm keeping on pushing on global collaboration. Now I'm going to switch tracks. I will now get into the theme, future challenges to software development. And I'm going to take some liberties because you had 4 days of science. All of you are researchers, scientists. I am not actually. I'll present the challenges I see as I see them, and hopefully we will have a dialogue, we will have a discussion. And I'm going to attempt something which I normally don't do because I'm not a very good storyteller actually, but I'm going to try and end with a story. Let's see how it goes. I'm attempting it for the first time, honestly. This came up, I don't know what happened to Ananth Raghunathan actually. In his presentation, he did talk about
Anand has to attend, he was invited to speak at the VLSI conference in Kolkata and he had to go for 1 day.
1 day, okay. Oh, you came, okay. We were wondering where you were. Okay. So I think this we discussed in the last few days actually. A computer with the capabilities of a human brain would consume 300 megawatts of power. Even with neuromorphic chips, it would consume probably 300 kilowatts, and brain consumes 23 watts actually. So, clearly there's a significant opportunity to experiment with understanding the brain, understanding the architectures, understanding the materials that are used, looking at new materials, new models, new architectures, everything. And so there is a significant opportunity for us to innovate, do research on, come out with better models of computing. That's the first thing. Second, I'm trying to state this in a way in which I can get the point across. If you know the how, that's the algorithm, you can program the computer to get the what. If you do not know the how, if you do not know how to actually encapsulate that in your program, and you're going to struggle. You can't get the computer to do it. And that's what is happening. We don't know actually how we recognize images. Now we're trying to figure this out. We're trying to use the computers to figure it out, but we don't know actually how. If we don't know the how, I think it's going to be quite a challenging with the existing model, which is based on finite state automata theory or automata theory and things like that, using programs, using programming languages to make the computer do what we want. And this is, in some sense, the evolution of computing. Computing was invented for process automation, to take tasks which are clearly defined and automate them. That's the current model of computing. And we are now trying to use the same model of computing where we don't know the how to get at the what. And that, I believe, is a big challenge. And it's to do with the evolution of computing, I strongly believe, and I'll come back to this. This is my story to end the talk, actually. A related question is, we are now getting huge amounts of data. Now, what does the data tell you? Now, again, because of the model of computing, if you know the question, you can actually write the algorithm and the data will tell you what it is supposed to. What does it contain? Whether it has the answer or not, doesn't have the answer. But if you don't know what the data contains, there's no emergent information that's going to come out of this, jump out of the data. But it does contain something, but we don't know how to extract it because we haven't figured this out actually. And again, it's, I think, the limitation of how we look at things today and the models that we've used to come to where we are today. I know these are larger questions, but that's why I said I will ask the questions and place it before you, and we need to probably tie this into the work that we do and see whether we can get at these larger questions to get answers. Next is actually the amount of legacy software and the problem of maintenance. And since I'm part of the IT industry, clearly this I see as a huge challenge, and this is only becoming worse. anything that's written, the minute it starts being used, it's a legacy software. Because from that point onwards, you need to maintain it. And the amount of software in the world is only increasing. And over time, I think all of us will become maintenance programmers. And we've already become, in some sense, we are spending at least 1 hour a week, maybe some of us spend maybe more than 1 hour a week tweaking our mobile phones. You know, there's computers and we reinstall the software, we install upgrades, we tweak with some of the features, we do all kinds of things actually. We've all become maintenance programmers. Imagine a world that is about 2.5 billion people tweaking their phones. Imagine 50, 60 billion sensor devices floating around. Now who is going to actually maintain all this? And I'm asking these in some way to illustrate the challenge again of the current model of computing. This is all setting up for the story I want to. So we are moving to a world of ubiquitous computing. You know, we will have computing everywhere, sensors everywhere. Our life is going to depend on these sensors. So in some sense, we created general purpose computer. From there, we are creating our special purpose computers. Then we are going into a world of sensors, smaller and smaller computers. Computing started small, became very large. Now we're going back to creating these billions of smaller computers actually, and we are going to tie all this together. The promise of this is every single human being who has an access to this connected world can sense anything that's happening anywhere in the world in real time. It's amazing if you think about that kind of power, because ultimately it's all going to be connected. So anybody anywhere or anything anywhere can sense anything else happening anywhere in the world. It's amazing actually. But do we know how to manage this and how we will make it work? And can we create an orderly world out of this amazing power that we're going to create? And we are already seeing the issues with security and things like that. Crime, war, every one of this is moving online. Now this is reported in press, so I'm just quoting it. Every single router which is sold in India has a backdoor trap, every single router. And even the manufacturer, Juniper, that's the case that was reported on paper, doesn't know that it exists, or maybe they say they don't know that it exists. Imagine this. Our life is going to be dependent. Our fridge is going to actually spy on us, or our washing machine is going to spy on us, our microwave oven is going to spy on us actually. Our mobile phones are spying on us. Everything is possible. Trustworthy computing, etc. How do we create order out of the world that we are going to create? So I said, okay, let me now start on my story. As I said, I'm not a scientist, so I didn't want to say theory of knowledge or something like that. So I said story. So it's a story, please. And as I said, first time I'm sharing, and so please take it as a story and think about it. And I'm going to paint the story of evolution. Everybody knows this is my crude way of putting evolution. Energy, from that something happened, matter came, matter atoms started interacting with each other, molecules were created, something happened again, protein molecules were created, suddenly life emerged, and life means they are able to replicate, create duplicates of themselves, reproduce themselves. From single cell we move to multi-cell organisms, animals, and finally man emerged. That's evolution till now, very, very quickly, 30 seconds. So I think when matter emerged, or maybe even energy we can say, is information. We have something there. It's literally unknown. We don't know what it is, but there is something there. But with atoms interacting with each other, and it's accidental, that's why I'm saying it's mutation in the beginning. You have some interactions and some things happening with information now. Information is starting to build on itself, actually. And when it comes to molecules, information is getting organized because they have some stability. They have, certain molecules are better than certain other molecules because they can survive, they can sustain themselves. And clearly with DNA, actually there is a lot more order at this point with the information that is there. And I'm calling this actually knowledge, actually. And this information, this knowledge is actually continuously evolving, changing. Now DNA is also in some sense a program, because that order that has been created is actually a program. And the way it maintains itself it's by replication. There's nobody actually involved at that point to create these new programs and replicas of it. And it's also creating new uses or new use cases of these programs by adaptation and by replication. And replication, because millions and millions of replications happen, mutation also continues actually. But this now, the theory of evolution says that those that survive are the better ones, and that's why they survive. They're better equipped to survive, and that's what is happening. So knowledge, codified knowledge, through adaptation and replication is actually creating a world of living beings, actually. Again, nobody is maintaining this order. There is saying it's a sustainable environment. It's a sustainable environment. It's very efficient because of survival of the fittest and the efficient use of resources and things like that. It's very efficient. And at some point, the brain develops. And with the brain, we add to this. So till now, it was through adaptation, replication, etc. We are creating new forms of programs, new forms of knowledge, etc. But now with brain, we have awareness and learning. And with awareness and learning, actually, we are able to now think about what does that mean. And we use this awareness and learning to actually think about how can we augment the capability of man. Till this time, they did not, none of the other, let's say, things there, thought about what to do with the knowledge. They were just replicating. They were not thinking about what to do with the knowledge. But man, because of awareness, learning, and thinking, now starts to think about what to do with my knowledge. And they're using the knowledge to augment their capabilities. And that's, I think, uniquely human. I think, we have had some examples of other forms of living beings trying to do that, but man has probably, because of the brain and the evolved brain that we have, started to do this much better and probably to a, let's say, level that we need to now think about, are we becoming too smart? I don't know. But from a knowledge perspective, initially with thinking, we created language, oral knowledge, so we now start replicating this knowledge outside evolution, outside natural evolution. And we can do that now even better with tools to capture knowledge and to transfer knowledge. Oral tradition is a lot more difficult, but with written knowledge, with books, and finally with computers, we have become amazingly good. So amazingly good that now we are replicating DNA. More importantly, we are replicating programs. Right? Now, if you look at, that nature is amazingly sustainable. With the diversity of living beings, it's a harmonious, sustainable world. To some extent, if you are a life form that's getting extinct, you probably will say no. But ultimately, it's managing itself in some way or form. There's some method here. But we, of course, with computers and things like that, we are starting to now replicate and create new forms of knowledge and ability to program, ability to edit DNA and things like that. And we're not, we will have a lot more of these elements, far more than number of living beings, well, number of humans actually, not number of living beings. But that that number is not something that actually matters to us in a, so, we have more bacteria inside us than outside or something like that, right? Millions of billions actually. But it's all in equilibrium, in balance actually. But we're going to create a world that probably is something that we need to think about, probably is not going to be that easy to manage. Clearly, if you think of DNA as a set of programs, there's a fantastic way of maintaining them. Nobody is actually going in and, until now, of course, we are now going to go in and modify them. And if you're going to go in and modify them, then what is because we will have now millions of variations of these modified DNA out there. We have had the problem of programs and the maintenance issue. Now we will have billions of these potentially modified DNA floating around, which we don't know how we are going to sustain and maintain and take care, and what are the implications of this. So this is the story I want to leave you with. Thanks to all the speakers, because this is my last opportunity to formally I want to thank all the speakers, and there are some speakers in today's session also. All the participants, I want to thank the key players who made this happen. Professor Bhaskar Ramurthy, who's the director, Professor Nagarajan, Dr. Partha Mitra, Mriganga Sur, Anand Ragnathan, the three chairs, and Srinivas Kumar, head of Computer Science Department. Thank you all very much. Very, very important. Every participant, I hope you will give feedback, you will give your comments. We want to learn from this exercise. We want to know how you benefited, what worked, what didn't work, and how can we make it better. Because I strongly believe in global collaboration. So I want to know how to make this better. Thank you all very much.